Chapter 5.8, the Fibonacci Sequence. In this chapter, we're going to be learning about another special sequence that isn't arithmetic or geometric. This sequence was created by a man named Leonardo of Pisa, also known as Fibonacci. He was one of the most distinguished mathematicians of the Middle Ages, and he's credited with actually introducing the number system that we currently use into Europe. Now, what is a number system? What does that mean? We're going to talk a lot about that later, but essentially, this guy, Fibonacci, had a big part in deciding that we count 1, 2, 3, 4, 5, and so on. But the thing that he ended up putting his name on, or at least that he's credited with, is this special sequence. 1, 1, 2, 3, 5, 8, 13, 21, and so on. So as we learned previously, when we are met with a new sequence, generally what you want to do is attempt to see, is it arithmetic, is it geometric, right? To see if it's arithmetic, we start by attempting a little bit of addition. So to get from 1 to 1, we add 0. To get from 1 to 2, we add 1. From 2 to 3, we add 1. Get from 3 to 5, we add 2. 5 to 8, 3. 5. 8. Clearly, this is not arithmetic because, well, we're not adding the same thing each time. There is no common difference. We can also test that it's not geometric because if I tried doing multiplication, well, this would be times 1, times 2, times 3 halves, times 5 thirds, times 8 fifths, and so on. Right? It's not going to be the same thing each time. It only needs to be different one time for me to say it's not geometric or it's not arithmetic. There is no common difference or common ratio. But let's take a look at this addition part from our attempt at seeing if it's arithmetic. We have 1, 1, 2, 3, 5, 8. Where that sounds familiar, doesn't it? It's right here. So in fact, the definition of the Fibonacci sequence is that we start with the first two terms as 1, and then after that, each term is the sum of the previous 2. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5, and so on. 3 plus 5, 8. 5 plus 8, 13, yada, 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 right? So this is just an interesting little sequence. It's not easy to write a general form the way we did for arithmetic and geometric, so why do we care so much about this sequence? Well, what's really interesting about it is how it relates to other parts of life outside of just math. So we're going to explore how the Fibonacci sequence actually shows up in a lot of places you wouldn't expect. The first is actually in nature. So in the middle of the 19th century, mathematicians found strong similarities between this sequence and many natural phenomena. The numbers appear in seed arrangements of plants and petal counts of flowers, the structure of pine cones and pineapples, in the number of leaves on a vine, etc. All of these places in nature, all of these things in nature happen to maybe coincidentally have these Fibonacci numbers. So for example, here I have 9 different flowers, all with a Fibonacci number of petals. 1, 2, 3, 5, 8, 11, 13, 21, and so on. So all of these are their natural state of the flowers. And sure, maybe I just picked out some flowers that happen to be those numbers, but the fact is that after doing a lot of studying of this, people started to notice that this is just how almost all flowers are. These numbers of petals are the average number of petals on flowers. Like, yes, of course, a petal can fall off and then we end up with 4 instead of 5, but there are very rarely flowers that have, by default, 4 petals or 7 petals. By default, most things in nature have a Fibonacci number of petals or leaves, or they follow this sequence with the structure of the pine cone, the number of the number of, it has to do with a ratio that we're about to get to. It's hard to explain, but the little chunks of the pine cone, how the numbers of those that you can see follow this pattern as well. But now, why is this? I don't know. Mathematicians haven't figured out why this would be, but it just happens to be like this. So isn't that interesting? But because of this property, that this is found in nature and all of this, we tend to associate this sequence with sort of beauty in general. And so we're going to get into something that actually Greek mathematicians figured out first, without maybe knowing exactly what they were doing, but this thing called the golden number. So the golden number, also called phi, is equal to the square root of 5 plus 1 over 2, which is approximately 1.618. So the golden number, which we write as this symbol phi, it's a Greek letter, or phi, depending on how you feel like pronouncing it. The golden number is the value obtained from the ratio of one term to the preceding term in the Fibonacci sequence, approximately. So as we head further and further up in the Fibonacci sequence, when I'm at the 100th term and the 101st term, if I take the 101st over the 100th, it's going to be approximately 1.618. If I go further and further, it's going to get even closer to being always 1.618. So the lower number's not as much, but eventually it's going to be about that number forever. So why do we care about the golden number? The golden number gives us the golden ratio. So in the line above, the ratio of the whole, AB, to the larger part, AC, is equal to the ratio of the larger part, AC, to the smaller part, CB. In other words, if I take AB, so that's this whole thing, divided by AC, the length of them, that's equal to AC divided by CB, the lengths. And again, why do we care? Well, this is for any given line. If I create these a line where this is true, then I take that division, that ratio ends up being 1.618. This is called the golden proportion. But again, why do we care about this? Well, the golden ratio, the golden proportion, the golden number, all of this comes in to architecture. It comes into standards of beauty. It comes into the human body, in fact. So the Great Pyramids of Giza, which were built in 2600 BC, the ratio of any side of the base to its altitude, the height, is very close to the golden number. Or in the human body, architect Le Corbusier, I'm going to butcher this, Le Corbusier, developed a scale of proportions for the human body that he called the modular. This was supposed to represent the proportional harmony of the human body. Within that scale, as you can see, that number 1.618 shows up as well, right? It's if the ratio between your head and your torso, or your torso to your legs, or etc., 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 to be in perfect harmony proportion, this number shows up. This wasn't just decided on. No one just decided that this was the number. It happens to be the number that came out after doing a lot of study of this subject, of what would be the perfect human proportions. Now, who decides on that? This architect, I suppose. But we're going to look a little bit further into maybe why this feels like the perfect proportion. So, this comes into what is called the golden rectangle. If the length of a rectangle over its width is equal to AB, A plus B over A, where, as we can see, we basically taken a square and then a little bit more. And so that we can get this golden proportion, right, where the length of one side versus the width of the side has this nice proportion to it. We've created a square within our rectangle, okay? If we can accomplish this where it fits the golden proportion, this isn't just any old rectangle, we have to create the rectangle so that it fits this proportion. And then we continue this pattern, we get a new golden rectangle where I can create a square where once again, this new rectangle I can then create another square right here, and it will have the same ratio, the size of this square to the size of this rectangle. It's the ratio that we like. The size of this square to the size of this rectangle, it's the ratio that we like. The size of this square to the size of this rectangle, it's the ratio we like. It keeps being this same sort of shape, just shrunken down a little, okay? So if we continue this, we get what is called a Fibonacci spiral curve, like this. Now, why do we care again? Well, the Fibonacci spiral curve tends to show up a lot in nature. It shows up, again, in pineapples and pine cones, but also most prominently in nautilus shells. But it also comes up in architecture. So quite often we can use these golden rectangles, the golden spiral, to compare to a lot of like old Greek architecture tends to fit these ratios. So Greek buildings, statues, vases, urns, and so on exhibit the characteristics of the golden ratio via using the golden rectangle. Phidias, where the name Phi comes from, was a Greek sculptor who especially used this. So we can see, here is a picture of, I believe it's the Parthenon, where the if we create this rectangle that is the size, it ends up being the size of like the length versus height of the Parthenon, right? It's a golden rectangle, and if we start creating each of the golden rectangles within this rectangle to create the spiral, we can see how it fits into the larger work. So the heights of the columns are the square within that rectangle. The heights of this sort of area, I don't really know what to call it, but this area right here fits into the proportion versus the height of the roof, etc. So we can also find it in a lot of other art. Art that is considered to be very beautiful often fits into golden proportions. Now, this one I have to say with a little bit of a caveat, because it's very common that people, once they know about the Fibonacci spiral, will just sort of place it on art and claim that it's there without really showing why it's there. So yes, we can kind of see this nice little spiral when it's placed on top of the Mona Lisa. We can see that her head is it's like the golden rectangular height versus where her eyes are versus where her nose is versus where her hands are, and it kind of fits into this shape. We can see that, yeah, this makes a little bit of sense, but quite often if you look up Fibonacci spiral in art, you'll see that people just sort of plop it on places and then just say, look, it's there, and even though it's reaching very far to say that it is. So it's not everywhere, and some people see it where it's maybe not. But it is strange how often it does actually show up, especially with artists who maybe weren't studying this stuff. So Da Vinci, who painted the Mona Lisa, happened to also do a lot of mathematics, right? He had a lot of studies in other fields. So it's very realistic to think that he did this on purpose. But plenty of artists who end up with these proportions within their artwork didn't do it on purpose. And yet it just comes out that way. Because this spiral, this ratio, tends to come out naturally. We even find it in music. So an octave on a keyboard has 13 keys, 8 white and 5 black, all of which are Fibonacci numbers. In Western music, the most complete scale, the chromatic scale, consists of 13 notes, another Fibonacci number. Patterns that can be expressed mathematically in terms of Fibonacci relationships have been found in Gregorian chants and works of many composers, including Bach and Beethoven and Bartók. A number of 20th century musical works, including, of course, one that was named after Fibonacci himself, Fibonacci Mobile, were deliberately structured using Fibonacci proportions. But it's probably pretty realistic to say that the Gregorian chant was not. So, how deliberate these things are, that's where the question comes in. Why the Fibonacci sequence? Why are these numbers showing up everywhere, with or without intention? So obviously, there's no intention to it in nature, it just sort of happens. A number of studies have tried to explain why the Fibonacci sequence and related items are linked to so many real-life situations. It appears that the Fibonacci numbers are part of a sort of natural harmony that's pleasing to both the eye and the ear. Though in the 19th century, German physicist and psychologist Gustav Fechner tried to determine which dimensions were most pleasing to the eye. This is probably where you may have heard of the Fibonacci number, the golden ratio before. If you've heard of it outside of just having seen the sequence maybe in a prior math class, then it's probably in this context that this guy tried to determine what the perfect dimensions were for, like, a human face, or a painting, or just anything that our eyes consider beautiful. And it was found, studying along with a psychologist, that most people unconsciously favor golden dimensions when purchasing various things, but also when looking at faces. If you Google golden ratio faces, a lot of celebrities you'll see have these proportions drawn along their faces, and it'll show that they fit into these ratios. And the more your face fits into the golden ratio, the more quote-unquote beautiful you are often considered on average. Now, of course, that's all subjective, and again, people will just plop these rectangles on people's faces and make claims that are a little bit of a stretch. But the point is that it's interesting that this ratio, it shows up naturally in nature. But then we also tend to really like to look at it too, in all sorts of things. That much is true. But why? Now that I cannot answer, and neither could this physicist and psychologist. Why? But it just is that way.